Thank you, Peter. Delighted to be here at Berkeley. It's a great place to visit and also share with you some of these things that we've been doing. It's good that these talks are at 4 p.m. so as you leave, hopefully some of this may be useful to you on your trip home. So you hopefully won't. So I should acknowledge a number of people, several students, postdocs, people from places like Infosys who worked with us, and NUS colleagues, and also several organizations that supported the initial pilots and also adopted the solutions subsequently, and also folks who helped the program by their generous monetary donations. So the topic is urban immobility, and it looks like this in an extreme sense. It's extreme from our point of view, but it's an everyday occurrence in Bangalore. This was in fact the starting point for me. I wasn't stuck in a bad traffic jam in December 2007 in Bangalore, somewhere like that. And then you look around to see what's happening elsewhere. This is China and buses, and this is the famous Japan and trains, the Shinjuku station. And the modes of transport are not really relevant. Congestion is just ubiquitous. Okay, and peak hour gets really bad, but some of them can last more than the peak hour. This is a 9-day long traffic jam in going from Beijing towards Inner Mongolia, and it's 100 kilometers, 60-mile long traffic jam. Okay. It's just nothing happened for 9 days. People are stuck, and you can see here people selling drinks and other things to while you wait, but it cleared in about 3 hours. So it's a very interesting phenomenon, and there are many things to do with congestion that I've become aware of while working on this. Things like phantom waves and stuff that people have looked at and documented. But when you sort of step back and out of it, out of one of those, being one of these people who's frustrated, to what is the cost of congestion, there's the Texas Transportation Institute puts out numbers. This is the extra amount of money and fuel spent by vehicles stuck in traffic. So it's not the cost of transportation, the time and money spent to get you from A to B. This is just when you're stuck. Added up across major areas in the US, this is the number. So as these numbers go, there are estimates. But other cities and other countries have been putting these numbers out, and they're somewhat similar, very big. If we could make a dent in these sort of numbers by, let's say, even 10%, is very meaningful. Okay. This doesn't take into account other bad things like emissions and accidents. And here I don't mean safety just in the sort of accidents, loss of limb and life. I also mean every day, many metros, people that are crowded, people come in, and some of them, like the London Underground, Delhi Metro, the platform is open to the tracks. There is nothing stopping you. For example, Hong Kong and Singapore have barriers. But in these ones where it's open to the track, the danger is that you could fall into the track because people keep coming behind you. So sometimes trains wait in the tunnel to let people who have been let off from the previous train exit the platform before pulling in. Okay, so lots of precautions are taken, and it just adds to sort of general slowness, loss of capacity. Okay. So if you look at what's the basic problem in these networks, is not difficult to say. That sometimes which are short or long, demand vastly exceeds supply. Okay, so it's difficult to build your way out of this. It's difficult. If this situation occurred in computer networks, we would not, not a big problem to add supply. It's very easy to drag wires or do other things. The cost in the transportation world is significant. It takes a lot of money and a lot of space, a lot of years to do these things. And so something must be done about curbing demand. Okay. And our work is, on the one hand, consider incentives, pay people money to curb demand. So instead of charging people to travel in the peak time, pay people to travel off-peak. Okay, that's what we did. That's one form of nudge engine. There's other things we've done with similar ideas on for wellness and recycling. I'll come to those during the course of the talk. This can coexist with penalties, so you can charge the peak time commuter and reward the off-peak commuter. And on the other hand, try to increase this with more data and perhaps mobile apps. That is, there's some supply and get demand shifting not in time but in space or other things like that. Okay, you can reach people. That's the point of those mobile apps. So nudge engines, getting into this, what are they? Well, the main elements, there are several things. This is from the Stanford program called CAPRI, Congestion and Parking Relief Incentives. This ran for 2.5 years. It was funded by the US DOT. This is for the commuters of Stanford University to nudge them to travel off-peak, both in the morning time when they enter the campus and the evening time when they exit the campus. Okay. Stanford could be potentially Berkeley, it could be a large other employer like, for example, Google or Facebook or anybody else that has a large collection of people coming at some, within a small amount of time in the morning and exiting in a small window of time in the evening, causing congestion. So cities and the company might be interested in incentive programs like this. Okay. So this is the screenshot of an account. I will come to that later. For now, think of this as like, if you're a frequent flyer miles program member, let's take as an example United Airlines. This is where you earn your miles and you go to some website and monitor your record of earned miles and trips made, and then you redeem your miles. Okay, this is very similar. Your behavior of times of arrival and departure are sensed. As appropriate, you get points for making sort of trips in the right time, and you get to monitor how many points you accrued so far, what status you have. So this is bronze, silver, gold, platinum, and how many dollars you won, and when was the last trip you made, and what to do. And there's some other, your friends are also involved. This is a fake account we created for demo purposes. This is rewards. This is money being given out by the program. It's a live ticker tape, and I will tell you how that works. And so there are some elements. There's many things, but I want to focus on three main things. First is the money. We paid out in the form of lottery. So this points that you accrued could either be redeemed deterministically, 100 points equals $1, or you could use that to play a game of chance. And that is like a sort of self-administered lottery. And the game of chance led to some winnings. Okay. The second element is friends. Money, in other words, incentivizes you to change your behavior, but also it's well known in many programs that if you have friends on the program and they do something, you have the effect of social influence. That's the second thing we'll look at. The third thing we can look at is the effect of personalized offers. As you exhibit your behavior, so we learned that you are more likely to travel off-peak on Tuesday and Thursday mornings, but unlikely to do so on Monday, Wednesday, Friday, or some evening times you have more latitude. Then we will nudge you for off-peak travel at those times. And it's personalized, so different people have different times that they prefer to shift and different amount of points that they might be needed. You might need to give them different amount of points. So that's what this is, personalized offers. These are the main elements. I will talk about that. Okay, but this is an nudge engine. Everybody okay with this? Just at a high level, because I'm going to dig into each one of them. So to begin with, let's talk about what is the reason for randomized rewards. What's the reason for paying randomly? Okay. So this is a well-known example in most economics books. Chapter 1 would be this, the two envelopes game. You'd offer two envelopes. One of them, envelope 1 has $1,000 in it, just deterministic. Okay. The second envelope has $110,000, and you can win this amount of money with 1% chance, and otherwise you win nothing. Okay, so the expected value here is 1100. Which one would you choose? Okay, so if I can just get a quick show of hands, who wants a $1,000 envelope? Okay, who wants the second envelope? Okay, consistent. I see you guys are consistent. Okay, so I've had a show of hands from David and Eva before, and they're consistent. Okay, so the second version is, everything is the same, the odds and stuff, the ratios of numbers are the same, but now it's like $1 on the one hand versus $110 on the other hand. If we can just get a quick show of hands as who wants envelope 1 now? Okay, who wants envelope 2? Okay, good. So if you looked around or if you've had a sense for the question, you kind of see that lotteries make sense. There's some things you can prove about this within the framework of expected utility theory. But I'll summarize it as saying when the stakes are low, players are more risk-seeking. So it makes sense to consider lotteries as for payment. And the question is, it's an experiment now. So what sort of numbers are interesting and how to make it work, right? And would it work? Okay. To give you an idea, the Capri program that we ran at Stanford, we were looking for 10 off-peak trips, 5 morning trips, 5 evening trips. And we had $1 per commuter per week to put into the common pool of money from which they would win. And so each trip was 10 cents deterministically. That would be envelope 1 if you made an off-peak trip. And for 10 cents, it's hard to imagine people shifting. Okay? And on the other hand, the random rewards side, you could win, you played a game of chance. It was basically snakes and ladders. And you rolled a die for 10 points a roll. And this piece made its way up, your piece made its way on the board. When it landed on tiles that paid you, you got paid. And the payments ranged from $1 to $50. And the higher status you had, the higher amounts of money you stood to win, and the lower status was just, you meant you won smaller amounts of money and smaller average values as well. Okay, so that was it. Now, but before we got started on all this, we wanted to test the hypothesis that random rewards indeed make a difference or are attractive. So I was teaching a freshman seminar course in spring 2010, and we ran this recycling experiment. In the state of California, you get 5 cents for returning this bottle and 10 cents for the bigger version, or it could be a can. And the question is, what if we took that recyclable and offered the deterministic value as well as random options? These are the sort of major denominations. Okay, all these are like denominations in which we have currency. But I didn't make the expected payoff for this random option higher than the deterministic option. Often you would do that because otherwise why would someone take a risk? Okay, but we just left it as 5 cents on average. And we got people, so this is freshman seminar, undergrads dressed up in soda cans. It was pretty exciting to work with them. It probably worked because it was an undergrad seminar. Hard to see it working in a grad seminar. And they lobbied people at the Sproul Hall equivalent at Stanford, White Plaza. And then we continued doing it for 9 days over a total of 18 hours at different locations to just get more people to participate. And what happened was the first version of this was offered like this. You came, you had 5 recyclables, let's say. That meant you had 5 goes in this game or 5 trials. And in this case, this person says, I want to recycle 5 cans or bottles, and I want to try each one for the $5 option. So they could win 0, or they could win $25, or some multiple of 5 dollars, right, in between. And then a MATLAB program would go and evaluate your chance of winning. So it would just sort of, there'd be this sort of the time it took, the think time for the program, and then you either won something or you didn't, okay? And you know, people came and did this for the first day, and what did we find? Okay, so the most interesting thing we found, just because we were all at the booth, was a person came with recyclables and just was texting. They didn't care to know the outcome of the game. They didn't participate in this. They wanted the random rewards as outcome, but you could have just advertised in the newspaper, like lotteries used to do, okay, lottery numbers, okay? We could have sent them an email. So we wanted them to be more engaged, okay? That's one thing we wanted to do. Second thing is, there's a problem here of trust. You know, the odds are supposed to be as declared, but how does the person, the user, how does the player have proof of this, okay? So maybe sneakily the system is just not paying them. And so second version was we made a game, and the $5 option, we showed them a 10 by 10 tile grid. So you were supposed to win $5 with 1 in 100 odds. That is 5 cents on average, okay? So that's why it's a 10 by 10 tile grid. If you had chosen the $20 option, that would have been a 1 in 400 chance, and that would be 20 by 20 tile grid. So the odds become very obvious to you as a player. This is actually separately interesting because there's this theory in economics called prospect theory by Kahneman and Tversky, which has found empirically through psychological experiments that humans don't quite understand very small probabilities, just the biases, okay, or heuristics in our mind. So this is just something to try and make it explicit. 1 in 100 odds, 1 in 400 odds, what is the difference? What does it look like? So some people did go to the $20 option, found 400 tiles, and then said, I don't want this. This looks like, you know, not easy to win. So they went back to the other option, okay? And so now you chose your 5 tiles like this. And then the system said you didn't win by revealing the tile behind which there was money, okay?
But I came close.
This happens. People think that is exactly that happened. I was so close, okay? And I think it's just some mental tick we have that this is material, okay? And now what did we find? We found that they were engaged. This is a student who came with some number of units, I think 70 or so, chose the $20 option. So this is how a 20 by 20 tile grid looked, and they drew a face with a smiley, okay? So this was sort of an engaged user. This immediately sort of clued us into this is the way to do it. Games have narratives. So the persons who were listed here, one of them is Coleman Fung, who's also a donor at Stanford. He and 2 other folks who are the inventors of Guitar Hero, the game, actually started seeing some of the stuff that we did for the other things and told us about how to think of designing games that have levels, have a narrative. So, you know, this is like a scratcher game. This is kind of the least interesting version, okay? But then when we did the Snakes and Ladders, they had those comments to make, and so we learned some things, okay, there as well. In case you're wondering, the way we solved the mystery of like the system cheating you, I mean, here it's still possible after you made your choices, the system sneakily picked the green tile to be different from yours, pocketing the money for itself. Well, the thing would be, if you were to literally go to a booth and do this, okay, like in a recycling, it's what's called a reverse vending machine, the system can simply print out its choice ahead of time before you make your choices, but you can't see what it is. You can see that it's printed on the paper over there, and that'll be shown to you afterwards, okay? So the system can commit first. That's a way of verifying that it's not cheating you, okay? So, and then there's the internet version of it, okay? So what happened, how did the recyclers decide to recycle? Several units went for the 5-cent option, unexpectedly for us, meaning this was seemingly, this is the, you know, zero risk option. This is about right. So this hints at a very convex sort of utility function at the low payoff regime. What happened, in fact, was 3 students came simultaneously, and they wanted to just recycle they all had roughly 200 bottles each, recycled it with us. We begged them to take it to the facility. In fact, they would have gone to the facility we said we will enter your numbers and everything, but we don't have space in our car to take all this much stuff. Okay, but we offered something and they said, no, you have to honor it. So we did, okay. We paid them money, we collected the recyclables, etc. Okay, so this gives you an idea of how random rewards help, okay, I hope. There's a more concrete exploration of this with the Singapore public transit program I'll come to. Now let me move to a second thing, social influence. How do your friends influence you? And there are two ways directly. One is recruitment. If a friend invites you, it's word of mouth marketing, less expensive. But what we found also is that it's not spam if your friend invites you. If we invite you, it's spam. Okay, so it's better to get your friend to do the inviting. Secondly, people, you go and try to do recruitment of commuters in a large public transit system. Unlike at Stanford, there is no mailing list. You can't sort of say, guys, we have a program, please come. So we found subsequently Facebook is a good mailing list. Seemingly now everybody else has found out that that's the case. But we didn't do any, we just want to advertise the program. But friends are good for this too. Like they will, invite other commuters, so you don't even run the risk of, it's a very well selected group, okay? Second is behavioral shift itself. So on the first one, quickly some numbers. We launched the Singapore Insinc program in January 2012 with 9 newspapers and, in the major languages, 2 or 3 TV stations and radio show, etc. We only had 3,500 people signing up, okay? And then Chinese New Year came and seemingly nobody's heard of this program because, there's only so much you can get out in one spurt of marketing. And so we just didn't know what to do until we decided to have not just to invite your friend by email, but rather invite your Facebook friend. So we made Facebook Connect, Google Connect, Yahoo, etc. Just link Gmail, etc. And we linked them, okay? On February 14th, Valentine's Day, we said, recommend a friend sort of, program, launched it. Rather immediately, it basically doubled in a further month. But the important number is this: how many of these people are now in the system because of friends? And you see that growing, okay? So this is sort of finding users through their friends. That's one thing. In this program, which is Steptacular, was a wellness program we did. This is not trying to get you to go to the gym, but rather to just get you to walk a few more steps. So the Accenture USA have 33 offices in this country, and their participants, employees were participants in this program, and they got a pedometer, which they used to upload readings onto this online portal that we created, and then I gave them points depending on how many steps they walked, and that led them to redeeming options of the deterministic or the random type, okay? So the behavior is just walking more. And what you see here is when the program launched, the average number of steps taken by participants is this blue line. This is across all participants. The program actually launched a month before this, I should say. And initially we didn't have any, again, friends option. We introduced that a month into the program. This is a truncated chart. And people who have friends in the program versus people who don't have friends in the program, you have this sort of a gap. Okay, that is, those with friends in the program have more likely to walk more. Okay, now this is sort of one-time sort of finding, and then it's social people more likely to walk more, and those sort of that sort of ambiguity has to be taken out. But we've seen this consistently in other programs, and I'll share those with you. So that's one thing. The second thing that happened, as well as this one, which is the more friends you had, the more you tended to walk up to a certain point. The moment you had more than 6 friends, this is across all experiments we've seen this. 7th or 8th or the 20th friend has no extra effect on your behavior change. The other thing we found was also people who have friends in the program tended to complete the program with a much higher chance. And this one is more interesting because it is the case that some people lost their pedometer. I think 28 people lost their pedometers. It's one of those things you carry here. And that means they're just not going to be in the program anymore. However, some of them rejoined the program when one of the friends invited them to friend them on the program. They decided to rejoin the program. Okay, so that was an example, and they even told us this by email that this happened. Okay, so that's the effect of friends. Okay, what I'll do now is to tell you a little bit about how this all worked, came together in the Capri program is one where it all came together. We're already finished developing the basic ingredients. Steptacular happened before the transportation projects, as did the recycling experiment. So this is how it came together in the Singapore project called Insinc, Incentives for Singapore's Commuters. And the goal was to incentivize off-peak travel. And we launched it as a 6-month university trial with our colleagues in NUS. And then it was interesting, and the government wanted to continue. So a company called Urban Engines was founded with some of the students and myself and others. And from July 2012 till summer 2016, Urban Engines offered this program, and then we got bought by Google Maps in summer 2016. And I will tell you the results for this duration of time for which we have analyzed the data. So around the time that we concluded, it was at least 400,000 plus registered participants, as well as companies. So a company could join the program, for example, some bank or hospital, and then the pot would be enriched for their commuters. Okay, in addition to whatever was the base, you could get more. The summary finding is that the shift in peak load is about 10%. So the program continues even now. Okay, it's actually now called Travel Smart Rewards. So how does it work? It's exactly like a frequent flyer program, but for public transit users. So you have the smart card, like we have in the Bay Area, the Clipper card. It's how you pay for your public transit system. There's an equivalent over there. And you tap into a station that the turnstile opens, you board, and you tap out on the other side. That creates a commuting history, which gives us some number of kilometers of travel. And for every kilometer you took this trip, every kilometer gave you a point. And if your trip was in the off-peak time, you got 3 or more points per kilometer, depending on status. That's it. That's the program. So it's very easy to explain. We actually found it very easy to explain this after we said, we just need to latch this on to look like a like an airline miles program. Everybody gets that. So the biggest problem with these things that we found is the ability to communicate what you're trying to do to a very large group of people with whom you're not going to meet face to face. So it has to be something very simple and very easy to understand. Okay, this was like the biggest challenge. Whether responses to their emails or even some personalized offers especially, we had to make them really clear. So then you went to the Insinc portal and you looked at your history of points earned and redeemed and rewards. So the rewards could be cash, and that whatever you won went back into your travel card. Or at Stanford, we even gave away tickets to the Rose Bowl game that in the Andrew Luck days this is Stanford and Berkeley, so I don't want to make a big deal out of it, but we were a fixture for a couple of years. And so the monetary value of this ticket is $75, but because of the scarcity, this was like gold dust. Okay, we had tremendous, we had people. So you know how Rose Bowl works is that you play until early to mid-December, and then you qualify around mid-December for the game at the end of December, early January. And so you really have a very short window, and mostly when the university is closed. So we had about 5 days to get people to invite their friends, like a recruitment drive. For 10 tickets, worth a total of $750, which we gave out as 5 pairs, people invited their friends, and we had a 17% boost in enrollment. it was amazing. Okay, so if a city wants to consider doing this, just go to your local sports teams. Those tickets are worth a lot, and they will be potentially happy to do it because it's in the public interest. Okay, so this is the program, and you're going to see a series of charts and numbers, but what are they? So this is the morning 5 a.m. time and noon, and this is the peak hour. So 7:30 to 8:30 is the peak hour. So follow the blue line. This is what people were doing in the 3 months as revealed by the travel card. This is the trips that they were making in the 3 months preceding joining the program. All we wanted to know was what time did their trip start, and what was the distance of the trip. Okay, and so this says what time did their trip start, the blue line. So you can see most of the peak times are like between 7:30 and 8:30. And the orange line is what happened afterwards, after joining the program. So in this case, everything is done as a percentage. So the shift is 7.5% off of the peak, as shown here. Now, this is for people who might have been already commuting off peak. So this is every person who signed up. Okay, this picture is people who traveled a little bit more in the peak time before they joined. So if they made 5 peak trips at least in the 3 months before they joined, that is 60 weekdays of commuting, then they were in this category. So this is a subset of users, or this is a subset of these users. And this is further subset. These people made at least 10 peak trips, and these people made at least 20 peak trips. Okay? Yes? Well, it's there, this plotted as a 5-minute bins. It's visible if you sort of break it down more finely. This set of people are sort of committed peak time travelers. They seem to just shift just essentially slightly before, and it's almost invisible in the 5-minute level that we've plotted this data at. Here, the last two is less visible, by the way, I should say. Here is less visible, but there it is definitely visible. In fact, you can see this orange thing is hesitating a little bit before it flattens before. That is visible. That's right. True. That's true. I agree with you. In fact, this became a little bit of so there's something else going on. Look at these guys, okay? So someone traveling here, 6:15, decides they're not even in the peak, obviously, but they like you only got the extra 3, extra points if you travel between 6:30 and 7:30, or 8:30 and 9:30. That's the shoulder hour. So everywhere else you got just 1 kilometer equals a point. In what's orange here, the orange zones is where you got 1 kilometer equals 3 points or 4 points or whatever. Okay. So if you're traveling at 6:15 and you took a 10-kilometer trip, you'll get 10 points. But if you shift it to just after 6:30, that now is going to give you 30 points. So there's an unintended bump here. Okay, that these people were already going off peak, they just decided to get that bump. Okay, so this is an example of how things worked. Okay, so the moral of the story here is that the more peak time trips you're making before you join, the more likely you are, the more you have to shift out off the peak, and that's what this is showing. You can also break it down by many things. Those who have friends, those who don't have friends in the program, those who play the random game, those who just trade for fixed exchange rate, short distance, long distance, various other ways. Okay, it's analyzed in both a paper and a student thesis. Now, this is for the first 6 months, whereas if you look at a longer period of time, this is all participants over a long period of time, versus those who were traveling in so the ones who are traveling at least 5 trips in the peak and so on. Okay, so this is how the same charts analyzed from the end of 2012 onwards. Okay, now this is a thing that shows how people with friends did. So those who have no friends versus those who have just 1 friend in the program, 2, and so on. So you can see that the more friends you have, the better off you are in terms of shifting out of the peak. Okay. I'll end with one last thing about this. So, you know, it's well known in the case of airline miles programs that, you know, if you're part of a miles program, you tend to, you know, the year before and the year after joining a miles program, you have usually more miles of travel, just, okay? Because someone is monitoring that and rewarding you for it. Could that be true, or is that true? Is public transit adoption improved or increased on account of you joining this program? That would be an interesting and good benefit. This is number of weekday morning trips on a weekly basis in the 10 weeks preceding your joining the program to the week you joined and subsequently. The average number of trips that someone made who didn't join the program made about close to 1.5 morning peak trips. And that jumps to about 2.5 morning peak trips. So, you know, it's a 2 on 5, so 40% jump, okay? So that's a pretty, you know, interesting and useful uptick. This is for people who had been in the program much longer. This is not, you know, people in the steady state, okay? That's how many peak trips, morning peak trips they make. So this is an example of someone who typically joins here and then sort of just climbs and hopefully over there, you know, long into the future, they'll join this red line. So this is sort of good in terms of making the public transit more sticky, okay? So I'll stop there with this, go to the next topic on how data could be used. I was hoping to show other things on, like, you know, there's very interesting things one can do about understanding how road usage happens and how to shift traffic, but also in public transit. So one example is apps like Waze are known to do this, but at the same time, a more centralized and systematic way could be undertaken. And you can see how that works in the case of public transit. But I don't have the data anymore, so I'll share with you New York City taxi data, okay? But underlying all this is a system we built, right? Not different from the kind of big data systems that we see people building either in the real world or in CS programs, etc. Systems effort. And we did that at Urban Engines. And our data was the GPS traces or package scans. So whether you're tracking people's movements or package movements or vehicle movements, they all sort of have some signatures that they leave on a map as they move, some breadcrumbs or breadcrumb equivalents. And so city bus, package in a truck, or a taxi, okay? So all these things are just signals that are collected and go into this thing in the cloud, and where most of the work really consists of healing the data. So it's not easy to snap all this to street. There are lots of gaps due to urban canyon type effects. So you have to fill it in and snap it to street and do various things like this. The challenge is really that you have like lots and lots of vehicles putting this out. Think of a system like Lyft or Uber where there are a few thousand vehicles, or the taxi system in New York has 13,000 taxis. There's a lot of data coming out rapidly, and at a systems level it's very interesting and challenging. So what we did was built the first module called Digital Replica. This is showing you the buses in Singapore, and the redder it is and the fatter it is, the more crowded it is. And in the screen currently, how many commuters are there, how many buses are there. So as you zoom into the screen, this would have gone down, and this have gone down, but you'll see more detail. And this is what's happening at 8:02 a.m. on a certain day, okay? So it really is this view, okay? And the interesting thing was, at the time that this was done, it was not easy to put more than 1,000 moving dots on a map. D3, the visualization, thing at the time had a limit. So working around that, etc., was interesting, and pushing it through like a Wi-Fi access, a laptop or a tablet was interesting, challenging questions. But you can answer questions like, for the user, eventually, which stations are crowded right now? Or show me all the slow-moving, overcrowded buses, okay? And so you could sort of just blot out the rest of it and just look at that stuff. Okay, that's an example of something you can do. That's why it's called a digital replica. You can sort of get this view from about 10 to 30,000 feet above in the air and look at it as if you X-ray down the subway tracks and so on, okay? The other thing you can do is this so-called database, movement database, and you looked at it over a certain amount of time over, let's say, this quarter of, like let's say the spring quarter of collecting this data. I want to know, this is an example chart here which says, I want to know in lower Manhattan, what was the speed of taxis in the very early morning hours, which is the red line, versus the peak hour. What's the difference? Okay, broken down by the neighborhoods. So this sort of thing requires you to take the map and put this geospatial data you can impose of the neighborhoods or zip codes and so on. You can superimpose, then break your data down by that. That's the sort of effort that this is. Okay, but you can answer this. But equally, you can also answer questions about the vehicles themselves if you have the data. For example, how many small fragile packages from some customer were broken during shipping? This sort of thing you can do. Okay. Or how do the new one-way roads reduce traffic congestion in the central business district? Okay. So this is what urban planning folks or transportation planning folks want to know. Okay. So that's how you could use these things. Now let me show you in the next 5 minutes some sort of what came out of this. Okay. Well, I also use this platform as part of a course I taught. So I'll tell you before I jump into the few things I'm going to show you, what are the set of things that one can do. And what a city is interested in knowing the answers to sometimes, right? So students looked at things like, because we have New York City taxi data, is every time you enter a taxi, that is, it's now hired, to the time you were let off, where did you enter and what time, and where did you exit and what time? That's the trip. And what was the fare paid? And this is only for payments made through credit cards. Cash payments weren't available, records are not available. And how much did you tip? Okay, if you've been in New York City, you sort of pick a number, or you enter your own number. Okay, whatever number you want to tip, what percentage of the bill. So that's the data. Now you could use this, and students looked at the UN General Assembly meets in September, and what happens to traffic around where the UN building is, and how does it shift and get diverted as seen by the taxis. These taxis are sort of this ubiquitous sensors. You can see how they, and you can get a sense for the general background traffic. And secondly, what happens during US Open? Okay, everybody wants to know. Okay, where do people come from? What hotels do they go back to? How many of them visitors? How many of them locals? Taxis give you a fairly good idea. Same thing for concerts, for example. What happens during the northeaster blizzard? Okay, how long was the city down? How long did it take to come back up? Things like this. Okay, much of this is in this thesis of a student who studied this data, as well as some class projects, including like wage earning and differences in how taxi drivers were disposed to giving rights to some neighborhoods versus not, things like that. So there's something else that is true. Almost all human movement in large metros is highly periodic. So this is one example of it. No matter what level you break it down, this is picking a neighborhood. Pickups from Midtown Manhattan. Mondays, Tuesdays, Wednesdays, Thursdays, Fridays, Saturdays, and Sundays. So if you look at the weekdays, measured in the thousands over a 24-hour period, so this is 0 hours and 24 hours. It's periodic, fairly consistently, across the Mondays. I'll talk about some exceptions, okay? And here are Tuesdays, and so on. And most weekdays look similar to each other. Of course, within the particular day, Fridays look more similar to each other than to Mondays. Weekends look different. Now, these are the Memorial Day holidays in our month, so they look different. But if you go to financial district, the figure is different, okay? But the conclusion is the same. That is, in other words, the numbers here are different, and as is the pattern. But again, it looks highly periodic. In fact, this periodicity is even more pronounced if you zoom into the peak hour. Not just for taxis, for bus systems, for trains, for everything. It's just more or less same people going from the same place to same other place to work, and or whatever else is governing our everyday behavior. Brooklyn. Implication is that human movement is highly periodic. This could be used for recognizing patterns and provisioning supply accordingly. So if you know that X number of people are expected to go from here to there on a given day, you make arrangements. You could make arrangements accordingly. It's even better than this. Like the Moscone Center here, has large events, 10,000 or 15,000. Sometimes people of very large numbers accumulate there for conferences. Depending on how many people were dropped there in the morning, and you could look at the evening and see how many, you have a rough estimate how many people are going to require rides to go back out. We did that for the Jacob Javits Center in New York, as well as for, the next topic I'm going to talk about, Madison Square Garden Knicks games. Roughly, you have an estimate. Okay, so you have this is called latent demand. It's demand that exists that's going to exert itself on the system. Okay. Yeah. All right. So then, I want to end on a sort of something funny, or I hope it is funny. We had this question: do fans tip taxi drivers more if the local team, the New York Knicks, win than when they lose? Okay. So you're going to now, the question on your minds is causation versus correlation. But wait until I get through. Okay. So what would you do? Well, we go to the map of New York, put a perimeter around Madison Square Garden, and say pickups or drop-offs before the game and pickups after the game. The game time within 50 meters of this place. Look at all the pickups. That's what you would do. That's what the system can do for us. Then we look at days when there were games, days when there were no games, days when the Knicks won and days when the Knicks lost. Okay. And if you run an unpaired t-test with a p-value which is sufficiently small, meaning statistically now is significant, when the Knicks won versus when the Knicks lost, there's 1% here difference, close to 1%, which if you normalize 19 to 100%, then it's actually a 5% difference in the tip. Now you'd be like, well, is this true? Is this like an artifact? Well, let's see, okay? I mean, statistical significance is high, so you would have to believe that it's true that people do tip more. But now, this is the nice thing about data. You can do better than that, as Cheng Wang did. He looked at the distribution of tips, what percentage of people tipping. As I said, in New York City, you enter, and you swipe your card at the end of your trip, you enter in a taxi, the default tipping option is 20%. They just expect you to be justly generous, okay? Now you, to show your extra pleasure, your lack thereof, have to physically choose the other options. So when the Knicks won, Knicks lost is the red thing and Knicks won is the green thing, like sort of bluish green. There's a bump at the 25 and 30% choices. So this is okay. So people are just deliberately choosing those options. And there's also a small bump on the other side on the days the Knicks won. So Cheng Wang hypothesized the losing team, fans of the losing team who don't like this. But what he fought, now with this sort of system, you can see, are they going to the unions, so what is that, Penn Station or one of the stations to like exit, in other words, are they, if they're fans for the losing, for the other side, maybe they're going to the airport or to a hotel, or where are they going after where the taxi leaves them, right? And they're going to the residential area or what? So he was able to follow up on that. So that's the sort of thing you can do with these systems. Again, as I said, this is for just to end on a hopefully amusing note. But the questions are serious, and I hope you're both encouraged and interested in this sort of thing. And this can be done for many problems that we have every day, and broadly gathered on this topic of societal networks. Transportation is one, energy grid. It could be water conservation, it could be anything else. So with that, I'll stop, and thank you for listening.
Questions? Did you ever look at how big the reward was versus how much shift there was?
Yeah, we did. How big was the reward versus how does the shift? There are papers summarizing, or theses summarizing that. Because the highest reward at Stanford was $50 and at a certain time in Singapore it was 200, then it was increased to 400.